All right. So the organizers, and thanks them for organizing this wonderful workshop. Charge me. I can start, right?
Sure. Yes, yeah. We'll switch gears. Vlad Skokov from North Carolina State University. We'll start talking about entanglement entropy.
You, Alexei. Okay, so what I'm going to talk about today is about entanglement. And specifically, I will kind of, talk about entanglement entropy for high energy collisions. But before I get there, okay, because it's quite a wide topic, I have to introduce you some basics. And for this, I will talk about classical information theory today and quantum information theory. So why I start from classical information theory? Just because it will be easier for me to build up on that so that I can talk about quantum. If I would just start right away from quantum, proving all these relations and theorems will be too complicated. Okay? So, but a lot of this, what I'm will be talking about in quantum part, can be understood by doing the classical information work. Okay, so and next tomorrow I'm going to talk about the application to high energy nuclear collisions. Specifically here, I will work in a some model which you heard already about it. It's saturation framework or color glass condensate, and I will discuss entanglement within this framework. Okay, I'm not going to talk about it generically. However, later on, if I have time, I will also review the literature available or where entanglement ideas and quantum information ideas were applied to high energy collisions. Okay, so that's my goal, and maybe tomorrow I will have to take a little more time than 1 hour. Now, all right. So because I also would like to cover some open questions and those questions that you can actually attack in your future. Okay, so but before I go to this kind of little bit educational topics, maybe somewhat technical, I would like to give you a teaser, okay, of what to expect here, okay, and it will be more physical rather than this bird language of quantum information, okay, and this teaser is the paradox of the Parton model, okay, so and it was first discussed by Dmitry Kharzeyev and Zhenya Levin. And the paradox is the following. Consider a proton wave function. Okay, a proton lives, I don't know, essentially forever, and is an eigenstate of the QCD Hamiltonian. It is a pure state. Okay, it's a pure state. And as a pure state, it has zero entropy. Okay, it has zero entropy. Yet, when we probe a proton in deep inelastic scattering, or in proton-proton collisions, or in ultra-relativistic, ultra-peripheral collisions at relativistic energies, what we see at the end in those collisions, in those experiments, is well described by the Parton model. But what is the Parton model? The Parton model treats the proton, or at least the part of this proton which it probes, as incoherent collection of quarks and gluons. And as a matter of fact, it even considers them in the first approximations as quasi-free partons, as quasi-free quarks and gluons. Okay? And this incoherent collection of these quarks and gluons does carry a non-trivial entropy. Okay? And it's computable, right? So, but nonetheless, it has a non-zero entropy. So how do we reconcile this contradiction? That the proton has zero entropy while the partons have a non-zero entropy. Okay, so and that's the question I would like to get to eventually, of how we can solve this problem. So the resolution will be hidden in quantum entanglement, but I will come to that later on. Okay. So, and now I will start with a little bit more technical stuff here. And this classical information theory, my slides are very detailed. I will be switching them quite a little bit, only because originally I prepared this in terms of the Blackboard chart, and then a few days ago, after looking at your YouTube videos of this school, I decided to make it in a slide form because the arrangements of the blackboards here is not optimal. Okay, so, but bear with me. If you have any questions, stop me right away. Okay, so information theory usually talks about messages. Okay, and for us physicists, messages do not really necessarily, the thing that we would like to be talking about. Okay, so but by any means, when I say message, you can think, and when I say like length of the message, you can think about this as a number of microstates required to uniquely describe your system. Well, you probably know what the partition function is. So the logarithm of the partition function will be equivalent of the length of the message, which I will be talking about. Okay, so just a number of microstates you need to describe your system. Okay, but I will be using the information theory language, and this is why I will be talking about messages rather than physical systems. But you can always map it back. All right, so now let's consider a message of length n. Okay, and it will consist of just binary digits, zeros or ones. Okay, so let's say 0 occurs with a given probability p0 and 1 with the one with 1 minus p0. Okay, pretty straightforward. So now the question is, how many bits of information can one extract from this message? Okay, let's compute this. I'm going to use your
Just press once.
Yeah, but I need to go down to.
Oh.
Okay, so so let's compute this. So if we estimate if the message is large enough, we can estimate the number of zeros that will occur in this message. Well, B will be the probability of this zero to occur times the number of symbols in this message, the length of this message, right? So it's n. The number of ones is p1 times n. So the number of distinct messages with this composition can be easily computed, right? And it will be just given by the binomial. Okay, so that's the answer, right? So the usual combinatorics. Using Stirling's approximation for these factorials that appear in this equation, we can simplify it, okay? We will just consider large n limit over here. And from this large n limit, we can reformulate our answer, okay, in the following form. It will be 2 to some power n times s. Okay, so let's see what n and s is. So s in this equation, once I do all these approximations, I can extract, and it will be just given by p0 times logarithm of p0 minus p1 times logarithm of p1. And this is the definition of the Shannon's entropy. Okay, it tells you the number of bits of information so the total number of bits of information that we will observe in this message is given by this exponent over here, n times s. Okay, and therefore s quantifies the Shannon entropy, quantifies the average information per symbol in this message. Okay, that's just by definition, by construction. We can see that from this simple equation that the maximum entropy occurs where the probability is equal to each other for both 0 and 1 to occur. Okay, by construction, this entropy as it's defined over here is larger than 0. Or or can be equal to this to 0. So why is it so? So let's look at these equations once more. Okay, this equation tells us something about the number of messages. Okay? The number of messages. And the number of messages cannot be less than 1 for any possible P0 and P1. Okay, and therefore, so on the right-hand side of this equation, 2 to the power ns, we cannot have a fractional number, we cannot have a number less than 1, and this limits what s can be, so it cannot be less than 0. It can be 0, then we will have only one unique message, but it cannot be less than 0. All right, so now we would like to generalize this, and this is where we're getting closer to physics. We would like to generalize this for an alphabet with k letters. In this case, it's easy to generalize. We'll get just the sum over the probabilities with which those letters occur. Okay, so now we have k letters. So we can estimate what maximum entropy can be. So the number of possible messages of the length n is k to the power n, and therefore from this you can find that the entropy is less than logarithm of k. And this maximum entropy can only achieve if all probabilities of these letters are the same, and these are given by 1 over number of the possible letters. Okay, so in other words, the probability is flat. I will use this fact about the maximum entropy further on, because when we will talk about maximally entangled state, they will be characterized by this maximal entropy, and this will be the key in application to high energy physics and high energy collisions later on. Okay, so remember this. So this is where the probability distribution is uniform, flat, then it gives us the maximum possible entropy. There is, of course, another way of showing the same thing. So what is the maximum entropy is, and it is based on Lagrange multipliers. I will leave this over here, so you can look at this later on if you want to see a more detailed mathematical proof here. Okay, so now we are going to a little bit make things a little bit more complicated. So now, when we transmit the messages, we can also have external noise. Okay. So sender sends some alphabet of letters, and in this case, I will just denote these letters by x1, x2, and xn. But what you receive might be different because of the noisy transmission. Okay, so you will get the letters yn to ym, and by the way, n might be even different from m. Okay, so some letters might be garbled, right? So and therefore, to describe this, we will have to use the notion of the joint probability. So, and the joint probability here will be probability that x was sent, but xy was sent, but yj was received. Okay, it's a joint probability distribution now. You can think also about this joint probability distribution as if you have two subsystems, physical subsystems, right? So one of them is described by P of x and another of P of y if they factorize. Or if they don't, then it will be just something mixed over here. So from here, we can construct marginal probability distributions. Okay, just by, for example, if you would like to know the probability distribution for yj, we will sum over all possible i's over all possible outcomes for our xi, observation, or in this case, the original symbol set. Okay, so why the marginal probability distributions are important? Because in the future, we will be talking about the reduced density matrices. And the marginal probabilities are classical analogs of these reduced density matrices, okay, of this quantum reduced density. So from what we have already, the joint probability and the marginal probability, we can construct what is called conditional probability distribution. And conditional probability distribution is just the ratio of the joint to the marginal, and it estimates the probability of xi sent but yj received. Okay, conditional probability. So now the question is, it's the same question that we had before. How many bits of information are gained after we receive this message of length n? Okay, so we review what we've done in the past, but now having the noise in this transmission channel. All right, so now for this, we are going to define conditional entropy. And conditional entropy, well, there are a few ways to go around this. So first of all, I will consider the entropy when my y variable takes a specific value, in this case, yj. Okay, yj. So in this case, the conditional entropy is defined as the sum with respect to I. Okay, my conditional, and next I essentially just replace in the definition of Shannon entropy, I replace the probabilities with conditional probabilities. Okay, so it's P log P, and this combination will appear lots and lots in our lecture here. Okay, so by any means, this is just the Shannon entropy of the conditional distribution. Okay, so and that estimates the uncertainty of the signal once yj is received. So now the actual conditional entropy is defined in the following way. You take the entropy for the specific yj and you average it with the marginal probability distribution P of yj. Okay. So now the claim is that conditional entropy defined over here is positive. Why is it so? Any ideas? So let me start by saying so that in this equation, the answer is positive. Why? Because this P is a valid probability distribution, and we already showed that it is positive. In this case, if I substitute the probability distribution into this equation, it will yield a positive result for the entropy. Okay, good. So now, on top of this, I'm building up this equation. But how do I do this?
Just an average of positive quantities. So
yeah, just an average of the positive quantities, and it's going to be positive again, right? So, and therefore, this object over here, despite the apparent complexity of its definition, is still a positive number. Okay, so starting from with the definition of the conditional entropy, I can perform a few manipulations. Okay, by any means, what I do, I just essentially substitute the definition of the object that I have. Okay, I had the marginal distribution probability. Well, I can substitute its definition. I have the distribution. Yeah, I have the definition of the conditional entropy for a given simple yj. I substitute over here. I get a bunch of terms over here. In some of them, things cancel, right? So this pyj, this guy over here cancel out. That's kind of nice. Additionally, I can see that when I consider the logarithm over here, which came from the definition of this conditional entropy, the ratio in this logarithm, I can just write as a difference of the logarithms, right? As a difference of the logarithms. So at the end of, I end up with this expression. So that one, well, again, so we cancel this with that. We have this numerator over here and times the log of the numerator. That appeared over here. And then another contribution will come from the denominator in the log. And here we have it as well. in this equation over here, when I sum with respect to I, okay, so this sum will give me marginal probability distribution Pyj. Or that this definition again of the marginal probability distribution. Because nothing is I dependent in the log, I can sum with respect to I and get Pyj. So at the end of the day, what I got, that the conditional entropy is given by the entropy of the joint distribution minus the entropy of the marginal distribution. And this is called chain rule for the entropy. Okay. And this will be as well important in when we consider it. We will consider the quantum systems as well. So now, okay, so that's the full equation over here. We've written once more. So now we already discussed that the conditional entropy is positive. Okay, and therefore this difference is also positive. But this is only true in for classical distributions, for classical information theory. And it will be no longer true in quantum mechanics. And this will be something unique to quantum mechanics and something unique for entangled systems. Okay. All right. So again, so if I consider a system which consists of two parts, okay, a system which consists of two parts, then when I compute the entropy of the entire thing and I subtract the entropy of one of the subparts, that gives me the conditional entropy. And in classical systems, this is still positive. It will no longer be true for quantum systems. Building up on this, one can define what is called mutual information. We are still answering the question, by the way, now about number of bits we receive when in this noisy transmission channel, right? We still didn't get to the answer. So the definition of mutual information is over here. Okay, so this is a formal definition. We will work with this first orange part of it, okay, to which I will just substitute the definition of the conditional entropy, okay, to get this more symmetric definition where the mutual information is just given by the sum of two marginal entropies minus the entropy of the entire system. Okay. So if we look again over here in the very beginning, so Sx here describes the total information content of my message without noise, right? Without noise. Okay, that part. While the conditional entropy or this difference tells me the information about X you still don't know after observing all the Y's. Okay. And this difference gives me the mutual information. And this specifies is the information about X gained by observing Y. All right, so now the theorem is that the mutual information is positive semi-definite. We'll come to the proof of this in a little bit, but for this we'll need to consider another helpful concept first, which is often applies in statistical analysis as well. And this is called relative entropy. And that's the other concept that I want to introduce. So imagine that in theory, in machine learning, or in experiment, you want to quantify the difference between the hypothesis and the actual outcome. All right, so you have a hypothesis, for example, for the probability distribution of all those x's to appear in your message. It's hypothesis, it doesn't necessarily mean that it's true. Okay, so, and theory, your hypothesis tells you that the probability distribution should be Q of X. In other words, well, xi appears with the probability qi, okay, defined through this function. And I, in this case, will run from 1 to s. But it doesn't necessarily, your hypothesis doesn't necessarily has to coincide with an actual distribution. The actual distribution, well, will have is different, let's say it's p of x, and therefore xi will appear with the probability pi. So now, after n observations, how sure can we be if the theory is wrong? Okay, can we quantify this? And the relative entropy is what quantifies this this question, or the answer to this question. All right, so to get there. So after n observations, a specific letter or a specific outcome of our experiment, xi appears pi times n times. Again, on average, that's always true. Where pi is the probability that xi will appear. Okay, so now let's compute the probability of this outcome, assuming that our hypothesis is correct. Okay, we have a sequence of, let's say, xi, well, x1, x2, x3, etc., etc. Okay, so then the probability for this sequence will be given by, well, this probability to the number of xi's to appear, it's pi to the power n. Okay, this we assume that our hypothesis is true, and this is why we have this prefactor. So that this product will give us the probability of the sequence. But additionally, we also need the number of distinct messages, okay, with these occurrences that the calculation we did before, and this is given by this prefactor as we had before. Okay, so the only new contribution here is this additional factor. So the last fraction we already approximated in the past for large message, right? It is given by 2 to the power minus n times, again, Stirling approximation, to the power of this Shannon's entropy. So, but now we want to approximate everything at the large n, in the large n limit, so we can approximate this as well. Well, this is easier. Well, there is nothing to really approximate. We'll just be rewriting this q to the power pi I as 2 to the power log qi, right? In this following form. And these are additional factors pi and n. So it's pretty straightforward algebra over here. And this is this discusses the probability of the outcome, assuming q is correct. Okay, and from this straightforward algebra, we can get the definition of the relative entropy, okay, which is essentially this this part of this sum over here. Okay, again, so written over here in terms of the ratio under the log. Okay, so look, I mean, how it's different from the definition of the usual entropy. We have additional contribution from the log of qi. Okay, and if you look at this function over here, you can notice that it is not symmetric under p going to q, right? It's not symmetric, as you can see, under p going to q. There is no symmetry. Additionally, from the construction, you can see that although this definition is not symmetric, this entropy, entropy that we will, the relative entropy that we will get is still semi-positive, positive semi-definite. Okay, and it is only zero if our hypothesis is correct. So in other words, the probability to observe those letters p equal q is equals to p. So now to answer the question that we had, if n times s is much greater than 1, so it's a large number, then that would indicate that our hypothesis is incorrect. If they equal to each other, then it's correct, obviously. Yeah. If the entropy is equal to 0, then obviously p, our hypothesis is exact. So additionally, sometimes in the probability literature, this relative entropy quantifies the distance between these distributions in abstract space, where the distance between the distributions. Okay, but I would prefer to use the narrative that I just talked about of quantifying.
One question: why do you multiply there by n? When you say much greater than 1 in the case?
Yeah, so this comes again from the definition that the probability of the outcome is about 0 would tell you that your hypothesis is wrong. For this, you need to get 0 there. Okay, good. So either S has to be very large. Okay. In other words, so n times S has to be very large. Okay, now it can be achieved by in two ways. Okay, either n can be super large and S cannot scale as 1 over n, or S can be super large and n is is not too large. But again, so there is this much of entropy you can get from a system. There is a maximum there. So in other words, the mathematical statement is that n times S has to be large, and the way you're gonna achieve it, it's up to you. But n times S has to get the 0 outcome, assuming that Q is correct. Okay, so now we can prove the statement about the positivity of the mutual information. Or in other words, we can prove that the total entropy of the system is always less than the sum of the entropy of two subsystems. Again, so we have one system which is described by two variables x and y. We can integrate one of them, obtain the entropy of the marginal distribution. We can integrate the other one, obtain the entropy, the marginal entropy of the other part of the system. Okay, and there is this equality that the entropy of the full system is less or equal to the sum of the entropies of the subsystems. Yeah. So this will be important in the future when we will discuss quantum physics here. Okay, so the proof here is pretty straightforward, and the template of this proof we will in future apply to quantum information too. Okay, so and the proof goes like this. So it's pretty straightforward. So you'll just we'll compute we'll consider a joint distribution P of x and y, and additionally, as a hypothesis, we'll consider that these two distributions Px and Py are just can be factorized in the following form over here. So in other words, our hypothesis will ignore any possible correlations between the subsystems, between x and y. Well, then we can write down the entropy, the relative entropy of P double slash Q, right? So just by substituting the definition of this, expanding the logs. So when I expand this product of these two logs that came from Q over here, from Q I substituted Q over here. If we expand these two logs, we will get the two terms, which will eventually sum up into the entropy of the two subsystems. And the first contribution over here with the minus sign will give me the Shannon entropy of the entire system. Okay, but we should remember, okay, first of all, this matches the definition of the mutual entropy. But additionally, we should remember that the relative entropy is always non-negative. And this is why we've proven that this combination is non-negative, or the mutual information is non-negative. And we've proven this inequality, which is also, by the way, called subadditivity. All right. So now we essentially covered all required components to move on to quantum information theory, through which we'll go a little bit faster because we already have some experience with the classical part. So in quantum mechanics, we always deal with probabilities, right? And this is why it is natural to work with probabilities. So the quantum analog of classical probability distribution is a density matrix. And since it's a matrix, it will complicate a little bit our calculations. So to move on, I will consider a specific setup. I will consider a system. The entire system will be, I will discuss as A times B. So AB will be my entire system, combined systems. And I will consider as subsystems of this combined system, subsystem A, subsystems B, with the corresponding Hilbert spaces, HA and HB. Okay. So now, if I consider, states of my system over there, the simplest case will be a product state, where the wave, the state vector of my system AB will be just given by the direct product of the two eigenvectors in A and B. Okay, this is the simplest possible case, but by any means, it's not interesting. There will be no entanglement between A and B in this case. So in other words, the measurement in A can be done independently of B completely. So that's not very interesting. In general case, of course, what we are going to have entangled space, this discussed by the eigenvector, by vectors psi AB, which belongs to this combined Hilbert space, but is not a direct product of the two vectors. And the states will be entangled, and measurements on A and B will be correlated. Okay, will not be independent. So, but let's step back and just still discuss a more generic pure state. Okay, for a most generic pure state, one can prove the following fact, that we can perform singular value decomposition and rewrite our pure state as a sum of direct product of eigenvectors in the subsystems A and B. Okay. So first of all, you can immediately check by tracing out either the B system or A system. You can directly check, or just finding the entropy. We'll discuss it later. Finding the entropy of the state, you can directly check that the entropy will be 0, and that will indicate that the state is pure. Okay, so when we do this Schmidt decomposition, again, this is essentially the same as what you would do in the usual linear algebra. Okay, so when you do the Schmidt decomposition, this psi IA is orthonormal state in the Hilbert space A, and corresponding for the subsystem B2. And if we have the normalized state over here, which we can always achieve by performing normalization, then the sum over this PIs, this coefficient in front, will be just equal to 1. And therefore, these PIs we can treat as the probabilities. Okay, we can just think about the probability for the I's state to appear. sometimes people talk about the Schmidt rank. The Schmidt rank is essentially the number of non-zero PIs. Okay, so now I would like to find the reduced density matrix of this state. I mean, to find the full density matrix of the state, all I need to consider is just this operator over here, right? So to find the full density matrix, I take two eigenstates in this direct product. I take two states, so psi, psi b in this product, it will be the full density matrix. Now, by analogy to what we discussed with the classical distribution, I would like to sum up with respect to one of the subsystems. Previously, we did the sum with respect to xi's. Now I would like to trace out, in other words, the system B. Okay? So, but when I trace the system B, what it means that I multiply by the basis vector. All right, so I am finding the sum by multiplying whatever I'm computing over here, and I am summing with respect to i's. Okay, so now I'm working here with a specific operator that I have. Okay, and for this specific operator, which we had on the previous slide, let me use J over here. For this specific operator that I had over here, I can just substitute it and compute what I will get at the end. And at the end, I will get the following, nice result that the reduced or marginal density matrix now is given by this sum defined by the basis of in the Hilbert space of the system A. Okay. The density matrix defined this way is normalized. You can explicitly compute this normalization. So again, if you take the trace of this density matrix, this part will just drop out, and you will have the sum over PIs. And as we discussed, it gives you one. Okay, the normalization. Then you can prove, well, just by observing here, essentially, that this density matrix is Hermitian and positive semi-definite. But again, so you can just prove by the observation. All the PIs are positive numbers. So another statement is that if you would like to measure on the system A alone, one doesn't need to know about the system B. But again, so you can do these calculations pretty straightforwardly. And this is where the notion of the reduced density matrix is important, because then if you compute this observable, again, your operator only acts on the Hilbert space A and nothing acts on the Hilbert space B. Then you can integrate over or trace out your B state, and all you will get at the end is a trace over the A Hilbert space, where you have the density matrix, the reduced density matrix, and this is why its notion is so important in quantum mechanics, times your operator.
And this is still the case where the systems are entangled?
Yes, yes. Again, so my operator here measures only things in A. Yes. So now, important question here when we discuss quantum entanglement is purification. So this is an important concept. So let's say, so what purification means? Let's say I have a density matrix, rho A, and it has three above properties. What they were. It's normalized. Well, the trace of this density matrix is 1. It's Hermitian. and it is a positive semi-definite. Okay, but it's normal density matrix. The statement is, the mathematical statement is that I can always come up with a complement to the system B, to the system A. The complement I will call system B, okay, that the combined system is pure, okay? So I'm talking about the non-trivial density matrix rho A, non-trivial one, not pure. I will always purify it going to a larger Hilbert space. Okay.
Can you please explain this again?
Yes. Now I will actually go to the equations in a second. Okay, but again, so if you have, let me just like try to give you some sense of physics in it. So if you have a density matrix which is not pure, it's a mixed state. It describes a mixed state. You can come up with a complement, with addition to the existing Hilbert space. So this density matrix is on the Hilbert space HA. You can come up with such a complement to that, addition to that, the Hilbert space B, such that the entire system will be pure. Okay? All right. So why is it important? I mean, of course, this is some type of construction. And by the way, this construction is not even unique. You can come up with many complements of for the mixed state to make it pure. Why is this actually useful? Okay, first of all, it is useful to prove many theorems in quantum information. We will talk about this later. But additionally, it is useful because it helps to model open quantum systems, which we deal on everyday basis. For example, when describing jets, we can see a jet as an open quantum system because we integrate out the parts that we are not interested outside of the jet code. Okay, and we lose information about the jet, quantum information about the jet. Okay, if you would like to discuss the jets, or evolution of the jets, if you would like to discuss the small x evolution that you that Yuri Kovchekov talked to you last week, I think. Okay, so then what we want when we want to discuss quantum open systems, it's unfortunately is not as simple as the unitary systems, right? So quantum open systems are described by the dynamics, which is not unitary anymore. However, if you would like to formulate it, for example, on a quantum computer, you would want to make the system unitary. And you are achieving this by this purification procedure. Okay, so if you want to, for example, formulate the jet involution on a quantum computer, you have to first purify the system to expand your Hilbert space in order to actually perform the simulations. And this is one of the most
What was the definition for mixed density matrices? I don't remember.
yeah. So for the I probably didn't give you a definition, but let me just give you a practical definition. So if you have a density matrix, okay, its trace is 1. Just for any matrix, that's true. For any matrix, that's true. So now, if the trace of the rho squared is 1, that's pure. That's pure. Everything else is mixed. In other words, additionally, so there is a, so if you consider an arbitrary density matrix, rho, in some basis, but let's choose this basis in such a way, it's a Hermitian matrix. And this is why we always can find a basis in which this matrix is diagonal. If in this basis, this matrix has only diagonal matrix, right? So it's we perform the unitary transformation, we get diagonal matrix in the specific basis. So if in this diagonal basis, the matrix has zeros everywhere, okay, except for one entry where it will have just one, okay, and then zeros everywhere else as well, zeros everywhere else as well, then this state is pure. And for this state, it's obvious that the trace of rho square is 1. If it's not the case, the state is mixed. Okay. A byproduct of this discussion as well, if you compute the entropy of this state, of the pure state, right? And how you compute the entropy, you compute the trace of rho times log of rho is a minus sign. That will be the entanglement entropy. All right, so it's essentially the Shannon entropy of the density matrix. We'll talk about this later. But if you compute about this this entropy for this diagonal matrix, because of the prefactor here, it will have zeros everywhere except for the only one. So the prefactor is non-zero for only one entry. It's when it's 1. But at the same time, when it's 1, the logarithm of this entry is 0. And this is why that the entropy of the pure state is 0. And if it is not the case, if it cannot be represented like this, the entropy will be larger than 1. But we will discuss this in a second. Okay, so so purification can be built exactly in the way as like in reverse way as we discussed a second ago when we traced out the subsystem B. So you can always come up with a supplement which has orthonormal basis beside BI. Okay, so and you can construct this direct product. Again, it is very useful. So this is actually, by the way, so this is generally quantum property. It doesn't have classical analog. So in other words, so we start with some probability distribution. Okay, we add additional random kind of component to it, these B systems. And in total, we will get the pure system. Okay, so in classical, we can't do that. If we start with some probability distribution, multiplied by the other probability distribution, even though there is a correlation potentially between these two subsystems, we will never end up with a total probability distribution, which will be trivial. Never. Right? So there is no classical analog to this purification procedure. Okay, so now let's talk about mixed states and reduced density matrices. So generically, for a general mixed state, okay, the density matrix will be quite complex. Okay, we will have this vectors in the basis in the Hilbert space A, basis in the Hilbert space B, but all of these different indices are going to be different, and our density matrix will carry all the sum with respect to all the indices over here. Okay, so generically, in order to describe all of this, you would have to have 4 different indices. So when we have, when we classically discussed these different probability distributions, the joint one, the marginal ones, analog of this will be of these guys over here, the marginal probability distributions will be reduced density matrices. When we take the generic state, the density matrix rho, and we trace the subsystems, we trace either B or we trace out A. Okay, this is generalizes this classical marginal probability distribution onto the quantum world. Okay. And this can be easily achieved by looking at these equations over here. So now let's talk about the Neumann entropy of the subsystem. So we have this reduced density matrix rho A. We can construct this thing which I discussed a little bit earlier. We can construct the trace of rho times log rho by analogy to the Shannon entropy. But why does it make sense? What does it make sense? Let's again go to the basis. Rho A is a Hermitian matrix. We can always go to the basis where this matrix is diagonal. Okay, and in this case, when this matrix is diagonal, I can rewrite this von Neumann entropy in the following form as just a sum after tracing out with respect to the basis. And it matches the definition of the Shannon entropy, right, of what we discussed before. Well, by this construction, we can conclude then that the entropy is positive semi-definite. It is zero only for pure state, as we discussed already. Additionally, it is we know that there will be a maximum of this, as we discussed in classical systems. And the maximum will be when our density matrix will be a diagonal one with diagonal elements to be the same everywhere, right? So it will have a uniform distribution on the diagonal. Okay. And this is what is called maximally mixed state. So maximally mixed state is where on the diagonal you have the same number everywhere. It will be important in the future. Okay, so now one can continue working with this concept. For example, if I consider a pure system, okay, and for pure system, again, we talked about this, the entropy of the pure system is zero. Okay, but if I compute the entropy of the reduced density matrices, I can notice that they are going to be equal to each other. Okay, by construction, because they are described by the same coefficients, pi's. Okay, and therefore the sums, the Shannon entropy of these pi's will give us the von Neumann entropy for this reduced density matrix, and they are the same. Okay, so even if two subsystems, so the two subsystems, so the statement is the subsystems of a pure entangled state have entropy, even though that the full system has a zero entropy. Again, so this has no analogy in classical or classical distributions. Okay, so now let's consider the property of this von Neumann entropy, which will be important for our further physics discussion. And this is concavity of the von Neumann entropy. So let me construct a new density matrix. So let's say I have two density matrices, ρ1 and ρ2. And I will construct a linear composition from these two density matrices by just looking at this algebraic equation. Okay. Where this parameter t here, I can change. It's just parameter. I can change, and it will change from 0 to 1. Okay, from 0 to 1. You can explicitly check that by introducing this parameter in this definition in this way, you can check that it will never change the trace of this density matrix rho. The trace of rho, normalization of rho, will always stay as 1. And since I introduce it this way, it will always preserve hermiticity of this density matrix. So rho will be Hermitian. And additionally, you can also prove, I mean, the way it is introduced, that it will be positive semi-definite. Okay, for the density matrix defined this way, there is the following inequality is true. Okay, so we would like to prove this inequality. To do that, we will first show that if I consider the second derivative with respect to this parameter t, it is always less or equal than 0. Okay, to do that, we'll just find first the first derivative. The first derivative will consist of two terms, right? So just look again at the definition of our density matrix. We are going to differentiate it. First derivative can hit this term or that term, right? And therefore, you'll have two contributions. So, and the two contributions are that the first term, where, okay, well, here the contributions are where I can hit the logarithm of the definition of the density matrix in the definition of the entropy, or I can hit the prefactor, right, when I differentiate it. Good. So now, when I hit the logarithms in this definition, it will give me just some prefactor. And what is this prefactor? Well, it's 1 over rho times rho dot, right? Rho dot, where dot is a derivative with respect to t. But what is this d rho dt? If I look at this definition over here. Yeah. Okay, d rho dt, if you substitute what rho is, then in this sum, so this part is not going to contribute, and you will get rho 1 minus rho 2, right? Contribution. And with the prefactor that you have in the front, the prefactor that you have in the front, you can prove that this term by construction gives you 0 as a trace. Okay? So only the last term is the one with which you have to work with. For the last term, we will perform integral representation of the logarithm. So the logarithm can be written in this logarithm, the operator can be written in the following form. You can prove this equality by introducing the upper cutoff and then taking this cutoff to infinity. All these integrals that appear in this equation, integral with respect to s, integrals that appear in this equation are pretty straightforward. And therefore, if we would like to compute the second derivative of the entropy with respect to this parameter t, we have to differentiate the entries in this integral over here. We have to differentiate those rho which appear in this equation. So the first term here is completely unimportant when you find this derivative. And the resulting piece, the resulting contribution will be just the trace of this chain of these operators. Okay, where I just differentiated this denominator in this equation. Okay, the chain of these two operators. But this chain of these two operators, I can also write by using the cyclic property of the trace. I can also write this in terms of these two products. So this first part, this operator times this operator. Okay, again, so I use the cycle property of the trace, and I carried 1 square to this side, split this factor into the 2 square roots, and I constructed what looks like minus integral of the trace of the operator squared, right? So that's some operator squared. But you can also prove that this operator is Hermitian because the density matrix is Hermitian. And therefore, what we have in this integral is minus trace of the x dagger times x. Okay, so the product of two of the Hermitian conjugate by operator itself, and this product is always positive. This trace of this product is always positive, and therefore we've proven that the second derivative of the entropy with respect to the parameter is negative. And this is true for the concave functions when we found this inequality, and therefore for this concave functions we have the following inequality for any value of t from 0 to 1. Okay. So now let's consider a specific case of this where we can make connection to physics. And specific case is where we consider a construction like this. Let's consider a density matrix, like generic density matrix, in a given basis, let's say. And in this given basis, let's extract only the diagonal components of this density matrix. Okay? And that will be this entry over here. And the rest of this, of the density matrix, okay, the actual density matrix will be multiplied by T in this construction. Okay, so this construction is such that if I compute the resulting density matrix at the parameter T equals 1, I will get the full density matrix. And if I compute the density matrix at parameter T equals 0, I will get only diagonal components of the density matrix. So in other words, it's a linear interpolation between full density matrix and only the diagonal components of it. Okay? So it's an interesting construction which kind of decreases the role of diagonal components in the density matrix. I mean, this density matrix is, this row of T is well defined. The trace of this is always 1, Hermitian, and etc., etc. Additionally, one can compute explicitly that the first derivative with respect to the parameter at T equals 0 of this combination of this of the entropy of this density matrix is 0 exactly. So the proof is pretty straightforward. I'm not going to go through that in the details. So, and what we will establish that the first derivative is 0 at 0 parameter. Additionally, the second derivative is always negative or not positive. And additionally, one can show that the second derivative at 0 is negative, unless rho is diagonal to begin with. So I will leave you to prove it by yourself. And for any other times, right, as we discussed, so this is true. From here, if you just plot the function which satisfies this requirement, okay, you will establish that the density matrix computed at the parameter T equals 1 is always less than the density matrix computed at the parameter T equals 0 for this specific construction. But what does physically this, what does it mean? That dropping all diagonal elements always increases entropy. Okay, so you have a density matrix on a given basis. So let's say you ignore the off diagonal elements. Okay, the entropy, when you compute the entropy of this procedure, will be always larger than the entropy of the original density matrix. Okay, so we call this entropy the entropy of ignorance. In the experiment, oftentimes we cannot measure all diagonal components of the density matrices. Okay, just our operators, we will discuss this later, are constructed in such a way. And this is why we ignore something. And by ignoring this, we lose the information and we increase the entropy. And this is mathematical proof of this increasing the entropy. Okay, in the remaining 4 minutes, I'm going to quickly talk also about conditional and relative entropies. Okay, building up on what we discussed before. So conditional entropy is just defined by the analogy to the classical conditional entropy. In other words, conditional entropy is given by the entropy of the full systems minus the entropy of the subsystem. Same way as we discussed before. So the conditional entropy for quantum systems, in contrast to classical, can be negative. So remember, we discussed that this is always positive for classical systems. For quantum systems, that's no longer the case. An example, when it's no longer the case, consider that my entire system is pure. Okay, that means that the entropy of the full system is 0 exactly. Now, the entropy of this subsystem is always greater than 1, and therefore the conditional entropy will be given by minus the entropy of the subsystem, and it is a negative number. And that's always the conditional entropy only in quantum systems can be negative. Okay. So now let's move on here. So now, if we consider quantum mutual information, or in other words, again, so we build in this up by analogy with the classical information systems. Okay, it's very difficult to actually justify the name for this if you consider information in the quantum world. So this is just the analogy. Why this mutual information has this name is just by analogy with the classical systems. One can actually show that this combination is always positive. And it is zero only if our density matrix is a product state. So it completely factorizes between the systems A and B. And what it does, the quantum mutual information, it quantifies the total correlation with classical and total correlations between the subsystems, and the both correlations are both can be both classical and quantum. Finally, there are a set of important inequalities for the entropies. I will just list them. The proofs are written below them, and they are available on Indico. If you are interested, please take a look. So one of them is that that there is a minimum entropy on the full system. So SAB, the entropy of the full system, is always greater or larger than the absolute value of the difference between these two entropies. And this is actually saturated for the pure state when S equals B, when the entropy of the system A equals to the entropy of the system B. Then in this case, SAB can only be zero. Right, because here we have zero on this side, and then this will be saturated. Okay. Additionally, we have strong subadditivity. To prove this equation over here, you have to perform purification. I'm not going to do this over here. It takes a little bit more time than we have. So, but I will just list it over here as a fact. If you consider now that the full system, now we have three parts in the system. We have part A, B, and C. If we split this, if you said that the system is pure, we can actually rewrite this inequality in an equivalent form through the conditional entropies. And this fact is often referred to as a monogamy of entanglement. We will not be able to talk about this here. I want to mention this is often an important discussion in quantum information. Again, so it just reiterates over here about the monogamy of the entanglement. All right. So with this, let me also mention quickly quantum relative entropy that we need to do. We need to have it in the future. So if we consider two density matrices on the same Hilbert space, okay, we can define two density matrices on the same Hilbert space by analogy again. With the classical relative entropy, we can define quantum relative entropy as the following combination. Again, it's just an analogy with the classical expression. We can prove that it is always positive. It's very straightforward. Just go to the basis where rho sigma is diagonal, and here is the proof, is one line proof. And from this, we can also prove that the relative entropy is only zero if the density matrix is coincides. And additionally, one can prove an interesting equality, which is the monotonicity under the partial trace if we have subsystems too. Okay, I'm not going to go into these details. Some of them are discussed here on the slides, and they can be proven pretty straightforward. So here I'm going to stop, because in the future, what we are going to do, we are going to apply what we learned from this, okay, all these basic concepts to high energy scattering. Okay, but this we are going to do tomorrow. Here.
I guess for the this helps solves the paradox introduced at the beginning.
Yes, but go ahead.
because like you're not accounting for some entropy in one of the subsystems.
Yeah, so the idea of the solution of this paradox, let me actually go to the slide where I discussed it, because I partially outlined the resolution here. The idea is the following: that when, for example, a proton is probed in deep inelastic scattering by a high energy photon, this high energy photon has virtuality Q. Okay, so and therefore it only probes a finite part of the proton. Is approximate, so area of this finite area of the proton, and the area is approximately 1 over q squared. Okay, so we have the full proton over here, but we are probing only this shaded part, this radius of 1 over q. Okay, so when we want to discuss, we can treat this, the entire thing, as the system AB. That is going to be entire thing. The system that we do not observe, I will call B. So this B is a white part. The system that I do observe, I will call A. So the entire thing, the entire proton, is discussed by the density, described by the density matrix rho AB, and is pure, as we discussed before. But now I'm obtaining from this density matrix, I'm tracing this with respect to the P Hilbert space. Okay, the rest, what I don't observe, right? I do not probe in the DIS experiment, and I will obtain the density matrix, the reduced density matrix, rho A, and it doesn't have to be pure anymore, right? And generically, it's not pure. And if this procedure done in appropriate way, by taking, many confinement properties in the proton, etc., 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 you indeed will get most likely some the density matrix of what would be the density matrix of the Parton model, and that will carry non-zero entropy. Okay, so that indeed resolve this paradox. Right now, how to get to actual resolution of this mathematically. So this is the idea, of course, how to get to the resolution of this. This is a multi-step problem which has not yet been solved. Only because, in QCD we are dealing with confinement, and that becomes complicated. But in principle, at least we have a project for the resolution. And I will talk about this tomorrow, about all the subtle points in this discussion.
So as you change the resolution, wouldn't the size, density,
the amount of the number of degrees of freedom will change, right? So in principle, if I go to very large resolution, I will probe a proton as a single entity, and in this case, I will not have any entropy.
Can you describe this evolution of scales and within this formalism?
Oh yeah. You mean that can I describe the evolution in Q space?
Yeah.
For example, evolution of my density matrix. Yes, you can do that, and those evolution equations were written down. Additionally, you can also ask a different question. So if I would keep 1 over q to be the same, but instead I will go to higher and higher energies of this deep inelastic scattering part. In a sense, this is also equivalent to making the resolution kind of larger, right? So the number of degrees of freedom changes when you go to higher and higher energies. You probe more and more fluctuations in both. So here will be more fluctuations, here will be more fluctuations, right? So you're also changing the systems. And this can also be discussed. And it is discussed by small x evolution of the entropy. And we will talk about small x evolution of this entanglement entropy in the future.
I have a question on the relative entropy
Mhm.
you showed. So suppose I have the following scenario. I have one probability distribution, which I consider as the exact one. but this is for some reasons too difficult to access it. So I have two approximations of those, two different approximations. And now I can use the relative entropy with respect to the original one to decide which of the approximations is better.
Yes, yes.
And basically, the closer I get to zero, the better is the approximation of the original.
Correct. So there is another name for the relative entropy. It's called the divergence. And divergence means, how these two probability distributions diverge from each other, right? So, and indeed, it qualifies the distance in the abstract space between two different probability distributions, right? When the probability distributions are the same, then you'll get zero for the relative entropy. By the way, so just going back to your question again, this is true, of course, when we discuss this as a fact of the principle. But when we talk actually about physics experiment, the number of observables that we observe in our detectors is always limited. And I challenge you to observe any quantum phenomena in your high energy, nuclear scattering detector. You only observe momentum, number of particles, maybe some correlations between the particles. But all of these things can be quantified by one single combination, which is essentially trace of your density matrix times maybe a bunch of number density operators of different momenta, right? The Q and etc. etc. They can be like as many as you want here. But these operators are always diagonal if we talk about the number of particles in the final state basis. These operators are always diagonal, probably diagonal components of this density matrix in the same basis. Never they can probe all of diagonal components. So now one can ask, and therefore somehow you're not, when you measure things in the experiment, you are ignorant of what happens with all diagonal density matrix. And that will give you additional boost in entropy in the final state. This ignorance, this loss of information, as we discussed by this entropy of ignorance. So the combination of these two facts, the entanglement and the fact that we lose information in actual experimental measurements, gives the entropy of the final state.
Try to come back here at 1:30.
Yes, yeah.
Better.
Yeah.
Oh, I'll stay here.
Stay here.
I haven't eaten but will.
Oh, really?
It's okay.
Sure. Very busy man.
I know.
No lunch. Break or something.
I have to reschedule it from 10 to noon 15 only because of the
Oh, so this was your constraint, actually.
only because
Need a table to sit.
oh, you there is
Now, shut the door.
yeah.
I leave it here. Yeah, I will shut the door and.
Right.
Yeah. Yes. andiamo, attraversiamo e poi noi esatto, esorcizziamo Wings, sì, vediamo un attimo. No, non passiamo davanti a uno. Non credo perché è allo studio di amministrazione. Allora, we have stations not my bad. I think I have a virtual box that I read.
Yeah.
What? Okay, yeah, I just. think I. You can live here.
No, I think it works, but it's good to, if it breaks for you, I don't want to pass out a bunch. Have a good lunch. I'm thinking tomorrow we can make one food. There's no barbecue, so we'll have to give extra time to get lunch.
Okay.
And so if we end now, 1:30 is an hour and 15 minutes, they're gonna have to go across the railroad to like a subway or something. Yeah.
Oh, yeah.
Yeah, so yeah, we may have, so we should say goodbye to you now, and then, yeah, so.
Tomorrow, then.
Sure, right, yeah, okay, yeah, I'm just,
Goodbye, Lecture.
well, just, yeah, because, yeah, because
Yeah, that's.
Yeah. Yeah, because I mean, they're asking me about it. And,
Yeah.
there's not a good way to collect them. And it's like $25 a card if they don't turn in.
Right. Now let's do it. Let's do this.
All right. So I need a picture with this guy. Actually, we need a picture of all three. Michael, can you take a quick picture of this?
Let's go there in front of the.
Friday?
Thank you.
Saturday.
He's gotta go for lunch. Oh,
No.
oh, you want it in front of the sign?
Yeah.
Is that all right? Sorry. Thank you. Attorney's off over. See. Is the recording off?
Turned off the. I was talking.
Doesn't have. Fine structure.